Okay, so welcome. So welcome to the lecture discussion on RC filters. So what is an RC filter? Well, let's just talk about filters first. What's a filter, dude? Well, you can think of a lot of things that you're going to filter. I mean, first thing I think that comes out is air. So you're going to have this thing, just like this filter that filters air. It takes particulates out of air, or more specifically, it filters in, but like there are six different things in the air. I don't know. One is some kind of particle. There's a dust particle. There's a I don't know whatever. There are five different things in the air. I don't know what they are, but when they go through, it leaves a bunch of things in the filter, and then the air that comes out is kind of cleaner, right? It has less of that other kind of unwanted stuff in it. Essentially, you want clean air. Hold on a second. I should just stop drinking my tea. You want clean air, but it has all these particulates in it. So that's just air. What about water? Oh yeah, for sure. Lots of things we filter out of water. Okay, cool. What about like hydraulic oil? Yeah, for sure. What about like pneumatic? Oh yeah, pneumatic. There'll be filters in pneumatics too. So we want just the clean air. What about kind of wait a second. What if you were in a noisy room, like of 100 people, and they're just all talking, okay? But you actually want to, let's say there's one guy in the room, like his name's Lars, and he's got like a loud voice. Or what if there was someone in the room, maybe there's someone in there with a really high-pitched voice, or maybe a really unique kind of special voice. You're like, oh, that's Bob talking. You can always know it's Bob. But there's some kind of acoustic characteristic of Bob's voice, okay? And you know, you got this whole room, right? And then your brain can actually filter, oh, that's I can hear Bob talking over there. And you can almost even filter out what he's saying, even if there's 100 people talking. But you know that hum of 100 people talking in a room or more, and this is you can't hear anybody. But if you were to take all of that, and if somehow there was a very unique signature about everyone's voice, could you somehow filter out everyone else's noise and only get that person's signature? Actually, you could. And you do that actually electronically, or you could actually do it digitally, but we won't get into that. Or the other way around is maybe you wanted to hear Bob's voice only and you didn't want to hear anybody else's voice. Yeah, I mean, these types of filters actually exist, but I mean, I'm going to get into this a little bit more into like our control stuff. Okay, well, what about this? Let's say we have a vibration sensor. You know what? I'm going to grab a vibration sensor. This one's really cool. This is a really cool vibration sensor. Hold on a second. You'll love this. This is a really good example. I don't know if you can see this, but inside in here, there's this little ball that, I mean, I'll just jump. I'll move it and it moves. Okay, so there's this weight in here and it vibrates like this. Now, the interesting thing is that capacitance is the concept of an electric field, right? So we have two pieces of metal at a certain distance from each other, and there's an electric field between them. And we know that the charge that we can put into those two metal plates is actually proportional to the distance of the plates. So if I were to put these two plates beside each other and put a certain electrical field on either side, or just, you know, positive and negative, and then I were to move the plates, physically move the plates, actually there'd be a difference in capacitance of those two plates. And that's actually what's going on in here. I'm going to move this. There's this little ball that's bouncing up and down, but there's this long metal, kind of a piece of metal that comes down here, and then this is metal as well. And as this moves around in here, actually the capacitance between here and here changes. Now, I can create a really sensitive circuit, and by the way, later in this course, we will actually be developing really sensitive circuits to make sensors. Well, I had a hard time with that word. What's that word? To make sensors. Okay, cool. So what's going on here? Let's just get back to the filtering concept. Now, I've got this thing. Okay, now I've built a machine. Okay, I've built a machine, and that machine is vibrating. It's got a little bit of a vibration to it. Okay, and I want to sense that vibration because depending on how fast the motors and the shafts and the things and stuff that are spinning in the machine are moving, the machine is gonna kind of shake, or it's gonna have this shaking frequency that's either gonna be more or less. But it's gonna be kind of like this, or like this, or like this. But it's not gonna be like this, right? Let's just say I had a machine, right? And it was sitting on something else, like a moving vehicle. And that moving vehicle is going down like a dirt road, and it's it's all over the place, right? But the machine itself that's sitting on that vehicle that's moving down the dirt road, it is vibrating. And I need to know how much that machine's vibrating, because if it goes outside this vibration, like if the shafts and stuff, if they get out of balance or something and they start really kind of shaking, the whole machine's go boom, 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 and it'll shake like a washing machine. Dude, I don't want that to happen. So I'm going to build a sensor, and I'm going to put that sensor on that machine, and it's going to be vibrating, right? And it'll be fine. And it's going to be vibrating like this. And there's going to be some sensor somewhere that's sensing that vibration. But you know what? What about the car going down the road? This thing is sitting on top of a car going down the road. And the shaking of the car going down the road is kind of a little bit, like, it's totally inconsistent. It's kind of, it's all over the place. But I just need to be able to somehow, like I'm listening to that crowd of people and I can hear Bob's voice over there, I need to be able to listen to just this. Electrically, this is giving me some kind of signal. It could be like an AC signal. Actually, it has to be an AC signal, because filters don't work unless it's an AC signal. So I can take this and I can kind of put it into some kind of amplifier with some transistors and some cool stuff to actually make it give an AC signal. And that AC signal is just showing this vibration, and it could be a little bit consistent or a little smaller, but however it is, it's kind of got a specific frequency to it. Now, I want to target that frequency, and any other frequencies like that bump in the road, I want to get rid of those. So what we've just talked about is application for filtering out stuff. We started from just talking about filtering air, particulates from air. It's a concept you guys know. And then we moved along to kind of listening to that voice in that crowd. And by the way, if we did design a filter, if we took an RC filter and we actually used it to sense, to somehow listen and target just one voice in a crowd, we would actually do it exactly how we're going to do it today in lecture, when we're actually talking about this type of filtration system that we use with an RC circuit. And it's actually quite brilliant how it works. And it's, I don't even want to get into it because it's so amazing. So we've talked about application, and then I just gave you an example of some kind of vibration sensor. There are many other kinds of sensors that we use that give us AC signals. And even if they don't give us AC signals, we can actually turn them into AC signals so that we can put them through filters so that we can filter out all of the erroneous information that's coming in that we really don't want. I'll give you one more example before we go. I designed a, actually Rod and Jason were involved in this, so you guys will know what I'm talking about. You remember that that sensor that we put some sensors on our feet, right? And we were walking on our feet. We were walking along like this on our feet, right? And I wanted to track the motion of the feet, right? Now, we had all of these other things going on. What I wanted to do was I wanted to track different kinds of motion with the foot. Now, depending on the types of sensors we had, those sensors were also giving us the vibration of our body just moving. I mean, they're really sensitive, okay? So I could actually be talking and walking, and it may actually pick up my voice, or it may pick up little kind of movements in your kind of, let's say you're shaking a little bit. Let's say you have like Parkinson's or something, and you're shaking a bit and you're lifting your foot and you're moving it and you're going up and down. I still want to track that kind of, that larger motion. But if your foot is shaking, I want to get rid of that information. That's another place where we're using a sensor, and we're trying to censor out. Now we want to censor out the shaking, and we just want to get those larger motions. Sensing is, filtering goes on and on and on. It's actually used a lot in the audio industry and all kinds of audio machines, but we want to use it for control stuff because that's what we're studying. So what I'm going to do is I'm going to say, okay, good. There are lots of cool applications for filters, and a lot of them that you'll hear about like on the internet and stuff when you go study this stuff, it's actually going to be about sound. So I'll tell you one more thing before we get going about sound. If you ever use an EQ, an equalizer, I mean, I should, I'm not going to go grab my equalizer from my room where I have my stereo and show it to you, but an equalizer are those things with all those really cool channels along the way. They actually use RC filters. Actually, they use something called band pass filters. Pretty cool. But we're going to be using this application in control circuits, and more specifically in all the different kinds of sensors that we're using that are sensing information, and we get all of this extra information that we don't want. Dude, I just want to hear Bob's voice. Right. So we'll get into that. Yeah, your earphones for sure. Yeah, like I mean, I guess so. I mean, however, I don't know what an equalizer looks like. I'll show you. I'm not even getting into that. You guys look up an equalizer yourself. Audio equalizer. I've got one on top of my stereo with all the little sliders and stuff. So I'm gonna sip my tea, and of course, probably gonna make me burp. But I'm gonna share the screen now. I'm gonna go through the PowerPoint, and I need to talk about the math and the understanding. And I think I can tell you this now. The coolest thing about this is that the resistive nature of capacitors is frequency dependent. You had that like long pause there. Okay, the resistive nature of capacitors that we call reactance. Now, dude, like, I just gotta back up. I'm gonna talk to you guys. Like, this is like heart to heart stuff here. If you did not do the material from last week, if you did not watch the lecture, if you did not do the homework, and if you did not like just engage yourself with the material last week, you're going to be screwed. Because as we move forward in this course, you will not be able to move into the next class and fully grip the concept without knowing the material from last class. Cool. That was like the Uncle Lars and me just kind of giving you guys, straighten you out. Okay, good. So anyone here that hasn't done it, don't do that. It's like calculus class. You can't go to week 3 without going to week 2. You're screwed. Okay, moving forward. Going back to this concept, if you don't know this concept, jump back into the material before and learn it. The resistive nature of a capacitor is called reactance. Okay, reactance is dependent on frequency. It's frequency dependent, which is kind of weird, but I mean, it's pretty cool. I mean, if you go in last week, I hope you got that. If you don't, go over the material last week until you really understand that that was the key principle of last week, that the actual resistance or the resistive nature of a capacitor, and by the way, I'm only talking about when we use AC. When we use DC, well, the resistive nature of a capacitor is infinite all the time. It's resistive. I mean, for the first, as charging, it's not resistive, but after you charge it, it's just like a 100%. It's like an open switch. But if you have AC, the resistive nature of a capacitor is actually inversely proportional to the frequency. So the faster, the higher the frequency, then I've got this capacitor charging and uncharging, charging and uncharging, charging. It never fully gets time to charge, and it never gets fully time to uncharge either, discharge. So it's actually kind of like this empty bucket that you're almost filling and almost emptying, almost filling it. There's really no resistance. But if the frequency is low, you have all this time to fully charge your capacitor, and then it gets full, and then your voltage is still going up and up, even when your capacitor is filled up like 4 milliseconds ago, right? Or whatever, half a second ago, and it's full. So now it's full of resistance. The slower the frequency, the greater the resistance. Okay, now that's good. Now that's a concept from last week. How we're going to use that concept this week is the fact that voltage dividers, like, it's true. We're just going to do voltage dividers, right? This class is pretty much RC circuits is just a voltage divider. Although instead of having 2 resistors, there's 1 resistor and then there's a capacitor. And guess what? Depending on the frequency of the signal you're studying, the resistance or reactance, the resistance of the capacitor will change. Therefore, if you have a voltage divider and you have 2 resistors and the nature of 1 resistor changes, well, the voltage drop across that will change as well. Okay, yeah, and I'm not going to get into this too deeply because it's in the PowerPoint. I'll show it to you right away. So that's going to be the secret, the key to this. There are 2 keys to understanding this, to really grip this material. One is the fact that a capacitor, the reactance of a capacitor or the resistance, I keep using the word resistance, even though it's actually reactance, but when we use it in Ohm's law, we kind of see it as resistance, and we can use it in Ohm's law. So the resistive nature of a capacitor is dependent on the frequency, and it's actually inversely proportional to the frequency. And the other thing is that we know a voltage divider, we have 2 resistors, right? And the voltage in the middle that's coming out of there changes if one of the resistive natures changes. If one of these changes or one of these, that voltage is going to change. Dude, that is the total key to a filter circuit, and we'll just jump into that right now. So here we go. Share my screen. Share screen. Wait for it. Oh yeah, yeah. Share my screen. And all the math is down here. Oh, that's capacitors. Wrong week. I hope you guys watch this. This is really cool to see the capacitor charge. That video there, and I don't think it's that long. Anyway, here we go. So RC filters, and this is me doing the math for RC filters. So I'm gonna actually fly through the math slides on RC filters because, dude, there's me in action actually doing it. So welcome to these awesome things called RC circuits, where we need to fully understand that the capacitive reactance of a capacitor is inversely proportional to the frequency, and the fact that we can use Ohm's law and apply it in a voltage divider. So what we're going to do is we're going to study capacitive reactance review. I just already did that, but we'll actually see it in motion. And then we're going to take a look at putting RC circuits together. So one resistor and another capacitor that we will see as resistance, and we'll use Ohm's law. And we'll talk about something called impedance. What's impedance? I don't know. And then we'll talk about actually filters. What I need to talk about, we'll just go into impedance. But impedance is actually the total resistance of a RC circuit, as opposed to the total resistance of two resistors in series. We're going to look at the total resistance of a resistor and a capacitor in series, where this capacitor, the resistance of the capacitor, is frequency dependent. Here we go. So capacitive reactance, we know that capacitors are frequency dependent resistors. We know that at higher frequencies, a capacitor will appear to have no resistance. At low frequencies, a capacitor will have very high resistance. Now get this is interesting. At zero frequencies, or maybe just DC, the capacitor will have infinitely high resistance, because like as soon as you put electricity to it and charge it, it's charged. No more current can go in it. And you know the concept of resistance is the resistance to current. So if it's full, well, it's full. There's no more current flowing. And the resistance, or the opposition to the flow, is actually known as capacitive reactance. So this word reactance and resistance, I'm just going to use them intermittently, but I mean, it's actually called reactance. But we can actually use this concept of reactance and just throw it directly into Ohm's law, because, dude, reactance is measured in ohms. Yeah, pretty cool. Okay, it's dependent on the size of the capacitor. We know that for sure. Okay, no problem. And also the applied frequency. That's not a big deal. We learned that last week. That's a no-brainer. And it's based upon the capacitor. Sorry, the basis on this is the capacitor can be used to block or pass various frequencies in a variety of circuit configurations. This is interesting. This is kind of the key to this. This is what's going on, and we'll see this happen. So you don't understand this? That's fine. You don't understand the kind of last thing I said about how we're going to use this kind of as with the voltage divider rule and make that work? That's okay. You know what? You'll get it as we move through this. So let's move on. We know that this is the formula for the reactance of a capacitor. It's just 2 pi FC. So it's dependent on the frequency and the size of the capacitor. Okay, that's cool. So there you go, that 2 pi and FC. And then that's that. So let's just move forward. But I guess the one thing I want to highlight is it's measured in ohms, which is interesting. It's measured in ohms. And so is resistance. So we can use it in Ohm's law. Now, this is interesting that I'll get into this, because this phasor diagram concept is important, because when we actually study impedance, we have to understand that current and voltage are actually out of phase, which is really kind of weird. So this phasor diagram thing, we'll get into this as we go. But what I just need you guys to have an understanding of this, some of this terminology, we know there's V peak and V peak and V peak to peak. We know that at any point in time, I can find instantaneous voltage at any kind of point in this waveform. So this is a phasor diagram. We're going to kind of use this as we go through the course. I just kind of wanted to say that the time domain of an AC signal can be represented as a phasor diagram. We'll get into that a little bit later. But the thing I wanted to go here is that I wanted to go back to the original concept that I threw at you guys last week, was that this current and this voltage, current leads voltage. In a capacitor, current leads voltage. Now, in inductor, current actually lags voltage. In voltage leads current in an inductor. But I just want to focus on this. When we're dealing with a capacitor, as soon as we start to charge it, its voltage is very low, but the current going into it is very high. So the current is actually high and the voltage is low, which is weird. We're talking about just a capacitor in a circuit. At any time when the current's going through it, there's a voltage drop across it. If I were to actually study the voltage drop across a resistor and study the current through it, and if for some reason the voltage increased, the current would increase instantly. If I were to decrease the current would decrease instantly, right away. So the current, if I'm studying just the current in a resistor and studying just the voltage, they're always locked to each other in perfect phase. If the voltage goes up, the current goes up at the exact same time. If the voltage goes down, the current goes down at the exact same time. When we're studying the current, the AC current, through a capacitor, we're going to actually see that if the voltage increases, the current doesn't increase right away, and vice versa. They're out of phase, which is kind of weird. And we'll kind of see that, just believe me, with as we roll through this course, you're going to slowly kind of wrap your head around that and finally believe me, right? But if you really want to understand that a little bit more, go into last week's lecture and take a look at those curves that we were looking at. We would see that voltage and current are not connected. They're actually completely out of phase. Okay, going back to share my screen. Where to go? Here we go. Perfect. So there you go. So just this is the concept. We're actually going to use this. This is going to be a little bit of a problem for us because as soon as we use Ohm's law here, it kind of gets screwed up because we know that Ohm's law is all about the current through a resistor, the resistive nature of the resistor, and the voltage across the resistor, and then we throw that into Ohm's law and it works. But the problem here is, dude, the current and the voltage are out of phase. So can we use Ohm's law? Well, we can, but we have to be careful about how we use it and mindful. And there's kind of a way to get around that. And you'll see in a moment. Let's move forward here. Okay, good. So now, okay, the resistive capacitor circuit is one that, so a resistance or resistive capacitive circuit is one that contains both a resistor and a capacitor. And that's it. And it's interesting that the word load is here. And you know that a resistor is a load. I mean, you know that. You know, it actually is stealing energy. It's a load, right? It has resistance. Well, a capacitor is also a load, right? It acts like a resistor, and it does steal energy, quite a bit of energy, actually. So you can either put them in series or you can put them in parallel. I mean, just like we saw with Kirchhoff's law in series and parallel, we can use the same laws. We can use Kirchhoff's laws for both series and parallel. Looking at this like it's a resistor, we can use Ohm's law in this situation. We can use Ohm's law in this situation. Kirchhoff's laws apply here. By the way, we're always dealing with AC. We do not deal with DC. DC, all of this stuff we're talking about doesn't work in DC. It's only AC. Moving forward. Here we go. So the total circuit resistance is known as the impedance. Now, I know that's just a little funky for you, but let's just take a look at this. If I, and by the way, that's an AC, right? AC load. You can see it's all AC. If I just have this, that's just a resistor, and it's the total resistance of this circuit. Even if I put like another resistor in here, like I stuck one in here, the total resistance of that circuit is just total resistance of that circuit. I mean, if it was series, I just add up this resistor, pretending there's a resistor here, add up this resistor and add up this resistor, and then we're done. And that's the total resistance. Because the current through these are in phase and the voltage drop across these are in phase, and we know that Ohm's law is so very tied to Kirchhoff's rules and Kirchhoff's laws, right? I mean, we learned that last semester. Like without Ohm, Kirchhoff could not study what he did. He studied, all of his studies were based off of Ohm's law. So we can put a resistor here and a resistor here, and we can see that Ohm's law works for both. Over here, if we just have one capacitor, we know that the current through this capacitor and the voltage drop across the capacitor are out of phase. So how does that affect Ohm's law? Well, it actually does affect Ohm's law in a way, and you'll see how that goes moving forward. But just to complicate things even more, dude, what are we going to do about this? I know that the current through this capacitor and the voltage drop across, sorry, I just said capacitor. The current through this resistor and the voltage across this resistor are completely in phase. If for whatever reason, if I increase the voltage here, if the voltage drop across this increased, then the current through that would increase instantly. But the thing is, the voltage drop across this and the current going into this are out of phase. That's so weird. Before I move on to the next slide, I want to go back to something you might have thought as I was looking at this. And then I will tell you about this impedance. I did mention that the current through here and the voltage drop across here are in phase. So therefore, if I increase the voltage here, the voltage drop across this would increase and the current also would increase at the same time. Now, there's another way I can increase the voltage drop across this without touching this. And this is kind of the secret to this whole lecture. It's the fact that if for some reason the resistive nature of this changed, like let's say I had a potentiometer here and I just changed the resistance there, we know for sure that because of Kirchhoff's voltage law for a series circuit and the voltage divider formula, we know that the voltage drop across this would change if the resistive nature of this changed. So watch this. If I were to study just the voltage drop across this, I left this at the same voltage, but I changed its frequency, the resistive nature of this would change. So therefore, the voltage drop across this, the amount of voltage that this is sharing from here would change. Maybe, let's say this was 100 ohms, and depending on the frequency, this was 100 ohms. And then I got 10 volts here. I would have 5 volt drop here and a 5 volt drop here. No problem, I would. Ohm's law works. If I were to change the frequency and change this, and I changed it to 50 ohms or 200 ohms, the voltage drop across this would change. Dude, that is the secret to this. This is actually really cool that we have this. And we'll see this take place, and that's how we actually build a filter. Now, what I'm saying here is that there is a special way to add this resistance and this resistance, and we can't do it directly with Kirchhoff's, with using Ohm's law to actually say, and with the application of Kirchhoff's understanding of voltage drops for a series circuit, we can't just say the total resistance of the circuit is this plus this. We could if this was just a resistor. But because this is a frequency dependent resistor, the total resistance of this circuit is frequency dependent. So I can't just say, okay, so the total resistance is the resistance of this plus the resistance of this. Actually, I can say that, but because the resistance changes all the time, or it can change, somehow I have to create a formula that's got frequency in it. And guess what? We know that to calculate this, there is frequency. So there's probably some kind of way that we can actually do that. And it's actually graphically, and we'll see that in a moment. But again, let's just take a look at this. We've got here, the current and the voltage are in phase here. The current and the voltage are out of phase here. They're actually 90 degrees out of phase. Yeah, this is actually where kind of vector diagrams are starting to come in. Now, in this case, the current and the current through here and through here, by the way, the current through there and the current through there are in phase. The current that's going through the resistor and the current that's going through this capacitor are in phase, obviously. I mean, I can't have more current going through here and less current going through here. However it is, the current, if there's any current fluctuation at all in this circuit, it is seen exactly in both of these at the exact same time. What I'm saying here is that this is kind of trippy. This guy, the current and the voltage are perfectly 90 degrees out of phase. Perfect. Over here, but the current and the resistance, the current and the voltage over here are perfectly in phase. But over here, the current and the voltage, how they're out of phase is actually dependent on the frequency. Yeah, it's pretty trippy. And that, we'll see that mathematically, but depending on if this thing is at an angle that's like this or an angle like this, actually it's going to change the way that these are in or out of phase. Now, just believe me, we'll do the math and we'll move forward. But I want to let you guys know here when we take a look at this, the current through the resistor and the current through the resistor and the voltage drop across the resistor are in phase. But the voltage drop across the capacitor is 90 degrees out of phase. That's a capacitor. But the total resistive nature of this, it's got to have some new weird funky name. And we call that impedance. We call that impedance. So the total resistance of an RC circuit is called impedance. The resistive nature of just the capacitor is called reactance. And the resistance of the resistor is called resistance. Good. So there's a mathematical formula where we can put all these together and it just looks like this. And you might stop and you might say, dude, that's just That's just Pythagorean's theorem. It is. It's Pythagorean theorem, right? Because look, this is a right angle, and this is a particular angle here, which we don't know. But if we knew this value and we knew this value, then I could easily calculate this value, because in a right angle triangle, the square of the hypotenuse equals the sum of the squares of the other two sides. So the square of this equals the square of this plus the square of this. Dude, it's just basic geometry, right? And there you go. This guy is coming directly from the Pythagorean theorem. And I think just if you ever need to remember this formula, you are just being silly. If you ever actually need to try and remember what this formula looks like, you're just being silly, because dude, it's the Pythagorean theorem. A squared equals b plus a squared equals b squared plus c squared. A squared being the hypotenuse, a squared being this side plus b squared in this side equals this, or a squared being the hypotenuse equals b squared here and c squared here. Now, I've used E here because I need to kind of intermittently start to use E and V, because you'll start to see E more when we're dealing with AC voltages, more specifically because E is electromotive force, and E is the type of voltage that's created through AC generators, although it's also voltage. But because it's actually EMF, electromotive force type voltage, as opposed to the DC voltage coming out of a battery, you'll start to see E a little bit more often. So I'm using E here. And dude, that's just a simple formula. Now, by the way, if you need to know this angle, which actually we do, because this whole thing is dependent on the angle. If you need to know the angle, well, it's just the tan law. It's the inverse tan law. I mean, if you have a hard time wrapping your head around the inverse tan law, go back to your, grade 11 textbook. It's not a big deal. So if I wanted to know the angle here, I'm just going to use the inverse tan law of these guys here. Now, we had a question here, or a little pop here. How do we understand when the filter is high or low pass? Oh, that's a great question. I have no clue. No clue, Dave. So, dude, let me just continue, and you'll see you're getting way ahead of things. I need to do some hand holding. Just hold on a second. Okay, the impedance triangle. So this is where we're actually doing the math, okay? The impedance is actually this. This is called Z. The actual amount of the impedance is the magnitude of this vector, So the distance here, so essentially here, the voltage here is this. But you know what? The voltage and the resistance in this case are now in phase. Yeah, it's kind of weird. But I never really said voltage and resistance were out of phase. I said voltage and current are out of phase. But when we're using Ohm's law, we're going to use the Z, or the impedance. This value here is the number we're going to put in Ohm's law. Actually, we can use a bunch of them, but let's just continue here. What I'm saying here is that now when we're talking about Ohm's law, we're going to say V equals IZ as opposed to V equals IR. We're going to use V equals IZ. And this is going to give us the total current and the total voltage. It's going to study the voltage and the current. Even though they're both kind of a little out of phase, the Z kind of helps us deal with the fact that they're out of phase. So we're jumping out of V equals IR, and we're using V equals IZ, okay? V equals IZ. So no, and then the Z is essentially the Z is the magnitude of this guy right here. So so these are a phasor impedance triangles, okay? So these are these are voltage phasors to impedance phasors, okay? So essentially what's going on here is that this is a phasor diagram. This is a voltage phasor diagram, but the exact same things exist for the impedance phasor diagram, where we're studying just resistance. Over here, I'm going to take these, put these together, and I'm going to say, I'm going to take this vector diagram here. I'm going to turn this into a vector diagram here. I'm going to take this phasor and I'm going to turn it into a vector diagram. So we can see that the voltage and the voltage and the resistance of the resistance, if we use this phasor diagram, we can all see their relevance beside each other, or we can see them kind of in alignment together, so that the voltage and the resistance are perfectly in alignment together. Specifically, the VR is in alignment with the resistance of the resistor. The VC is in alignment with the resistive nature, or the reactance, of the capacitor. And the VT, the total voltage drop across this system, is in alignment with the impedance. Yeah, and then we turn this into a impedance triangle. I need you guys to start drawing these things because that's important for you to know how to do this. So here we go. So this is just this is what we're looking at. In a series RC circuit, by the way, it's series. It's important that we understand we're talking about series circuits. In a series RC circuit, the total impedance is the phasor sum of R and XC, okay? So this is the total impedance here, bam, right there. And to do the math, well, here you go. This is the math here, right? So this Z, remember before, over here, I was just talking about voltage. But over here, we can see that the resistance is perfectly in line with what the voltage does. So I can use Pythagorean's theorem over here, and I can find the magnitude of Z just by throwing it into this formula where this is the resistance and this is the capacitive reactance. And then Z is this value right here. So that is the total resistance of this RC circuit, although we call it impedance. And you'll see this. I mean, it's important to understand this because we're going to start to use the voltage divider formula. And in the voltage divider formula, there is a total resistance somewhere. Yeah. And we're going to see that we're actually going to use Z instead of the total resistance. Here you go. So impedance summary. Okay. Z is the impedance of an RC circuit, of a series. Actually, it's also the impedance of a parallel RC circuit. But right now, because we're using filters, we're going to talk about series. So Z is the total impedance, which is like the total resistance, but because it has capacitive reactance in it, which is dependent on frequency, we have this like new weird name for it. We call it impedance. Impedance is the opposition to the flow of current, just like resistance. Ohm's law still applies as long as you're dealing with this guy. Ohm's law doesn't work so well with this just XC, although there are applications for it, but not in a series, not in a RC circuit. When we're doing Ohm's law with an RC circuit, we have to use Z. And this angle indicates the phase shift between the voltage and the current. And this angle can change depending on the frequency. Yeah, it's pretty cool because depending on the frequency, this value changes. So therefore, this gets longer or smaller. So that's going to change. Okay, good. In a capacitive circuit, the voltage and current are 90 degrees out of phase. In an RC circuit, it's dependent on the frequency. Okay, good. So let's moving on here. This is an example where I need to create the impedance triangle for this. So what I'm going to do is I'm going to create, I know this is 47. Someone told me that was 47. And actually, you know what? Someone did the math for me, calculated whatever the frequency was over here, and did the math and found that this was 100 ohms. Okay? So I'm just going to put an impedance triangle together, and I'm going to say that's 47, that's 100, so therefore this is 110. So the total resistance, sorry, wrong word, the total impedance of this RC circuit is going to be 110 ohms. Now, there's also this phase, this out of phase. So in this case, the current and the voltage are out of phase by 64.8 degrees. Okay, that's what's going on. Again, like I told you, depending on the nature of this guy, which is dependent on the frequency, this value changes, which will also change the degree in which the current and the voltage are out of phase. So this is just a really basic example, but someone was really nice and actually went ahead and did the calculation of this. Depending on the frequency, we know this changes, and they calculated it for us. It was 100 ohms, but sometimes you won't have that, and you'll have to do that extra step where you actually calculate the reactance of this so that you can do this. Here we go. So the following circuit, I've got this and this and this. I know that this guy is perfect. So Z in this case is the total impedance, but because actually there's no R, Z equals R. And it's weird that I would even say Z, but you know what? I'm just going to say it anyway because it's a basic circuit, but I'm going to say if there is no capacitive nature, but for some reason you still need to use the impedance triangle, which is actually going to be weird because it won't be a triangle because your angle is going to be 0. But you can still say that Z equals R. Just moving forward over here, we can see that these guys are in phase from each other. And we know that Z is actually going to equal to R, which is 110. And then the total current is this. Dude, I'm just using Ohm's law, but again, I'm using this Z, right? Because I'm assuming that I'm using the same formula that I would use for an RC circuit, even though there's no C in here. So essentially, if I draw the phasor diagram, I got 0 phase between I and V. So therefore, these guys, and the impedance triangle is just a line. Now let's take a look at just this guy, just this. Now I know that this the current through here and the voltage through here are completely out of phase, exactly 90 degrees out of phase. And in this case, my Z actually equals my XC. My Z equals my reactance. So in this case, the impedance equals the reactance. And I have some values here. I'm just going to plug these into some formulas. But in this case, I actually have to calculate my RC. I mean, my XC. Before, I just knew that R equaled XC. But now I have to do some math. Not a big deal. I do some math and I come up with this. Okay, so I got 15.9K. And then from there, I've actually got to go in, moving forward, I know I'm going to use Ohm's law, but I'm going to use my Z, okay? So, but in this case, this guy down here is the actual total impedance. In this case, the total impedance equals XC because there's no resistance there. So I don't have to calculate my Z because it equals XC because, dude, there's no resistor. There's no resistor. So I know that the current and the voltage are 90 degrees out of phase. So I can assume that my Z is actually just equal to my XC. So I can go ahead and put this and I can make it equal Z, and I can put this value, which I calculated here, where I have my Z, and then I have my current. And then if I'm drawing the impedance triangle, it's just a line going down. That's it. Moving forward, here's an example where I have both of these things. There is resistance here and there is reactance here. So my total impedance is going to have an impedance triangle. It's going to have an impedance triangle for sure. And I can see that here when I do the math, there's an impedance triangle there. But dude, I have to take an extra step here. My total C is going to be this. My total this. Oh, what did I just do here? This is the same example. Oh, no, it's not. My Z, this is actually not a correct statement. I should just pretend you don't see this. I have to take this out of this slide. That's not a very good statement. My XC equals all of this, and my Z equals my resistance and my capacitive reactance. And I can do the math, and that is my total resistance, or what we call impedance, and we call it a Z. Now I've actually got a theta here that I have to calculate, and that is dependent on this value and this value. It's dependent on the resistive nature of the capacitor, called the reactance, and the resistive nature of the resistor, which is called resistance. Now I have an angle. Now I can do the math. I can use Ohm's law as long as I use a Z, and I can find out how much current there is in my system. And I can draw my triangle. And my triangle is dependent on the resistance, not the voltage, but the resistance. So I know this is 10K. Down here, this is 15 because I calculated up here as 15. Again, this statement is incorrect where I say the total impedance is equal to the XC. That's totally a lie, dude. I need to remove that. It's actually, the total impedance is actually this. It's actually this formula here. So I should actually stick that up here. So here we go. So there's that. Now, before I'm gonna pause. Okay, just hang on for 1 second. Okay. So this is just another example here. We have a resistance here, and we have my capacitive reactance here, and I'm just going to go ahead and I'm going to calculate this. Now I don't know this. No, I do know this. Sorry, this is 960. So I'm going to put 960 ohms here. This is ohms. I'm calculating this in kilo ohms. So that's how many kilo ohms I have. Now that is going to be the value of this guy here. This is my Z. Because I know that's 1.2 and that's 0.96, or that's 1200 kilo ohms, and that's 960 ohms. And then when I want to know the angle, I just throw it into the inverse 10 and I get this. So, dude, before I go on to, this is just another example, okay? I'm just going to fly through this. Just, you guys can sit with these by yourself. Okay, good. So frequency variation. I'm gonna keep going, okay? Just then we'll stop, breathe. The only thing this slide is about, okay, we've just done a whole bunch of math. I know you're like barely following, and that's fine. Or some of you guys are on top of it, but you can watch this again. I just want to pause and I want to say, we know that this guy here is always going to be the same. This resistance, it does not change. It's not dependent on frequency. But as I increase my frequency, the capacitive reactance of the capacitor decreases. As I decrease my frequency, the capacitive reactance increases. So the frequency, as it gets lower, this angle gets lower. Sorry, as the frequency increases, this angle gets lower. This angle in here, if the frequency gets higher and higher and higher and higher, this value gets smaller and smaller and smaller and smaller, and this angle gets smaller. So the frequency and the angle are inversely proportional. As I decrease the frequency, my angle gets greater and greater and greater, and so does my impedance. Essentially, what can happen is if I have my frequency close to zero, the impedance will be close to infinity. And essentially, this angle will be 90 degrees. And the total impedance will be close to infinity, and there will be no current flowing. So essentially, what's happening is that as my frequency gets lower and lower and lower and lower, my current decreases because my impedance increases. And we know that makes sense because as I increase the frequency of the capacitor, its resistive nature lowers. As I decrease the frequency of a capacitor, its resistive nature increases. So that's what's going on here, okay? So this is known as frequency response of an RC circuit. This is kind of cool because I'm going to pause here and just kind of let you guys breathe a bit before we get into actual capacitive RC filters. But it's all based on the fact that all of this is frequency dependent. The frequency response, how an RC circuit responds to frequency, is that its total impedance changes and its capacitive reactance changes as we go. So before I jump into an actual filter, I just want to pause and let you guys just chill for a second. Any questions? Are we good? Do we want to just breathe? I'm going to sip a tea. Okay? So, yeah, it's a lot. It is, dude. It is a lot. But, I mean, that's why I record this, right? So, yeah. Yes, RC and R are always perpendicular. They're always completely out of phase. And the reason is this, because the R and the XC, right, the reactance and the resistance, are actually completely in phase with the voltage. Yeah, they're totally in phase with the voltage. So when we're taking a look at voltage and capacitive reactance, the voltage across the resistor and the voltage across the capacitive reactance, they're always going to be out of phase. They're always going to be 90 degrees out of phase, because essentially, if there's a voltage drop across the resistor, okay, then there's going to be current flowing through the resistor. We know that. The higher the current, the greater the voltage drop. Okay, that's good. We're good with that. In a series circuit, if there's really high current going through there, well, the only way that can happen is if the capacitor is empty. So if the capacitor is empty, its voltage is, well, zero. Because we haven't charged it. Zero. Right? So if the voltage drop across the resistor is high, that means there's high current. If there's high current, that means that the capacitor is empty. So therefore, the voltage drop across the capacitor is zero or really low. So if the voltage drop across the resistor is high, there's high current. And if there's high current in the capacitor, its voltage drop is actually really low. So high, low, low, high. Can I do this? Yeah, I'm having a hard time with that. But essentially, if the voltage drop across the resistor is high, the voltage drop across the capacitor is low. If the voltage drop across the capacitor is high, the voltage drop across the resistor is really low because there's no current, because the capacitor is fully charged. It's got a high voltage drop across it. It's fully charged. There's no more current flowing. So therefore, the voltage across the resistor is really low. That's in an extreme case where the frequency is so low it's close to DC. So in that, we can say that if voltage and if resistance are perfectly in phase, we know that the resistance of a resistor and the reactance of a capacitor are always 90 degrees out of phase. They're completely opposite from each other. They're inversely proportional, or in time, they're reversely proportional. Or more specifically, they're just 90 degrees out of phase. When we're looking at time, one is doing the opposite of the other. If one's high, the other's low. If the other's high, the other's low. So moving forward, I think we got to jump into the rest of this because I'm not sure how much time we have left in this class. And I mean, just go through this. I may fly through this. I'm sorry, but dude, there's a video here. So, and there's a really good example on the board of me actually doing this. So watch that. Let me just share my screen and we'll just finish this lecture off. Although I'm probably going to go at light speed again. 30 minutes we have left. Thank you, but 35. Awesome. I'm so pleased. You guys are like, you guys, I need you guys to be like my people that watch the clock. For some reason, I never watch the clock. I have no idea. I don't even know when the class ends. Everybody has their faults. Everybody's special in some way until 6. Okay, that's easy. I can remember that. Let's move forward. All right, awesome. Filter circuit, filter, woohoo! So we've got an audio source. We put a filter in there, and then we amplify it, and then we have a speaker coming out here. So essentially, this is kind of a situation where the audio source may be that crowd of people talking. And dude, I know Bob's frequency. I know his voice. I know it's very specific frequency. Maybe he like talks really low all the time, and you can just use a low pass filter to be able to pass just the low frequencies, and then you can hear Bob's voice. And all of the other people talking really high, you won't be able to hear. More specifically, dude, no kidding. If I did this, okay, I'm gonna take my F and my G. Yeah, I'm gonna take my G. If I were to do this, I can't really do this, but there we go. We play this at the same time. I don't know if this is going to happen or not. Okay, that's the best I can do. They're not designed to do that. But you can hear there's a high frequency and a low frequency. If I wanted to, I could design a filter that would actually filter out just the high, and you'd only hear the low. Or I could actually filter out the high, and we'd only hear the filter out the low, and we'd only hear the high. And we can do that with these RC circuits. It's pretty cool. So that's an example. That gave me like a little, what do you call, lightheaded? What do you call it, head rush or something? Yeah, it gave me a head rush. It takes me back to the first time I smoked when I was a kid. Anyway, that's a whole other story. Okay, let's go on here. All right, awesome. So here we go here. So this is a great, perfect example, dude. This is what's going on. So this is from my vibration sensor. My vibration sensor is tracking this. In this case, this is kind of opposite to the example that I was using. This is kind of opposite to the example that I was using. Don't pass out. Yeah, no, I don't want to pass out, dude. No, none of that. Well, I just lost my, what happened to the, I don't know what I'm doing. I think I just shared my own screen or something. Yeah, hold on, guys. Here we go. No, I don't want to pass out. So here we go. This is an exact opposite example. Remember I said I had my little vibration sensor, and I had that on my machine, and it's giving me this, and maybe I'm going over some road that has consistent speed bumps, and I'm just going over these. Dude, if I wanted, I could, this is the opposite of what I was talking about. This is the signal from my vibration sensor. And then this long wave is actually the wave that's actually the bumps in the road. Let's say I want to get the waves of the bumps of the road. I want that. Then I can filter that out. Now, this is a good example here, I mean, of actual audio. Before, really, we want to talk about vibration sensors. But in this case, let's just say this was an audio signal. Let's say this was just like a nice, just a nice hum, right? Now, I've got this. If I can do this. See if I can get this out of phase. I can't really do it in and out of phase. Can I do this? Can I bend this? Yeah, I can bend this. I can bend one of them, but not the other. There's like a high pitch frequency on top of that. I did it. Okay, there's a high pitch frequency on top of that as well. Sorry, there's a bit of on top of the. I don't know if you can hear that. If I had two harmonicas, do I have the same note? No. If I had two harmonicas that were not tuned to each other and I played them at the same time, they'd be like this. Whoa, 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 whoa. Maybe I want to tune that. Whoa, 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 whoa. I want to tune it out. I don't like it. I just want to get that, right? That frequency. I can actually use a filter to get rid of that. So let's go over. Wait, how come I don't know what I'm doing? Sometimes I don't know what I'm doing. How do you tune my harmonica? I take it to a guy who tunes it. Okay, so here we go. So let's go on. That's what you got to do. I take it to Newmarket. This guy in Newmarket. Actually, I buy all my harmonicas from him. Anyway, so here we go. So this is what's going on. So that's that whoop, 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 and this is the whoop, that long frequency. I can tune that vibration out if I want it. Here we go. So what's happening is this is kind of this is the actual symbol for a frequency. This is the band that is passing, and that's the stop band. Okay, so that's the band that's passing, and that's the stop band. How many harmonicas do I own? I don't know, 18 or something. I'm probably pushing 20. Here we go. So essentially, this is kind of a chart that we look at. And look, this is an FC, and that's just an F. So this is what we call the corner frequency. It's called the corner frequency. It's the frequency where the kind of the frequency drops off. The amplitude of the frequency drops off. Don't worry about it. We're talking about magnitude. So let's just continue because this is confusing. Let's just continue. Now, this is what's going on. Dude, this is a circuit. This is a filter. And this is important that we kind of stop and take a look. Take a look at this. This is a low pass filter. Low pass. So what's going on here is that we're passing low frequencies. So again, this is the frequency band, right? So from a low frequency to a frequency of about some value around here, what happens is the actual voltage, the amplitude of that frequency is going to be at a certain value, and it's going to generally stay pretty good until the frequency goes up, and then the actual output is going to go down and down and down. And the output I'm looking at is the output here. This voltage right here, this between this point and that point right there, if I study the amplitude of the voltage right here, what it's happening is that as the frequency increases, because I've got this RC circuit in here, as the frequency increases, the amplitude goes down, and then it gets to this point. Oh, 0.707? Huh, it's some value that we've seen before. It's not actually RMS, but yes, it does use 1 over the root of 2 for other reasons, which we won't get into. You can go study if you want, but we don't need to know that. We're not engineering. We're just using these things in application. So moving forward, as I increase my frequency, it gets to the point where it starts to dive down. It starts to go like, boom, and just totally dive. And we're like, okay, after that, what we're going to do is we're going to call that the stop band. Any value, anything that's coming out here after a certain frequency will be attenuated, will be lowered. The amplitude will go down. The voltage will go down. It will go down so much as I increase the frequency to the point where we can't hear it anymore, or there's nothing to censor it anymore. As the frequency increases, it senses nothing. But dude, why does that happen? I mean, let's stop here. Dude, I'm gonna stop here for a second. Let's just go over here. Take a look at this. If I just looked at this, okay, and if I put a particular frequency in here, okay, I know that this has a certain resistance, and that has a certain resistance, and we call this reactance. We know that the total resistance here will actually change. We know that as I increase the frequency, the total resistance actually goes down to the point where if I increase the frequency so much, this XC will become 0, and my total impedance will be equal to my R, because the frequency is so high, there's no XC anymore. Or if I decrease the frequency really, really, really low, then my total impedance is actually going to be really close to my XC, because my XC is getting almost to infinite because the frequency is so low. So this is going to go way down here. It's going to have an angle of 89.999 degrees. With that said and done, this is where the magic comes in. Dude, this slide is the magic slide. And you need to know the voltage divider to move forward from here. The resistance of this stays the same. The resistance of this changes depending on frequency. It's inversely proportional to the change of the frequency. If I lowered the frequency down to like 2 hertz, like really, really low, the resistance of this would get enormously high. It would go into the mega ohms. If I had, now just think about this. Forget about that this is a capacitor. Forget about that that's a resistor. Just say these are 2 resistors. This is, say, 1,000 ohms, and this is a mega ohm. This is 10 volts. What's my voltage drop across of this resistor going to be? It's going to be pretty close to 10 volts. I'm just going to say that again. This was 1,000 ohms. This was 1,000,000 ohms. And this was 10 volts. I studied the voltage here it would be 9.9999 volts. Because this being so much, it's being, if this is actually 100,000 times more than this, because that's a million and that's 1,000. This is 100, so the 100,000 times more than this. So this is going to take so much of the voltage. This thing won't have very much voltage drop across it at all. This will take all of the voltage drop. The voltage out here will be really high. So in this case, if my frequency was low, the output would be really high. Okay, that's fine. Okay, so if I put a low pass filter in here, I would get high voltage out. I mean, sorry, if I put a low frequency, I would get a high voltage out. Now we'll do the opposite, and you know what's going to happen. If I increase the frequency, so it's like, I don't know, like 100,000 hertz, 500,000 hertz, a million hertz, like it's really high. The resistive nature of this is going to go down to like 2 ohms, like, or 1 ohm or 0.5 ohms, like ridiculously low, which means that if this is 1,000 ohms and this is 0.1 ohms, this is 100,000 times more than this. So therefore, the voltage drop of this is going to be, the voltage drop is going to be all across this. I'm going to get really low voltage out here, and really, so if I studied the voltage drop across this resistor, it would be 99.99 volts. If I studied the voltage drop across this, it would be 0.001 volts. If this frequency was really high, this would be really low. Oh yeah, of course you can use multisim to simulate this, dude, completely. So there we go. So that's dude, that is the secret. And to actually do the math with this, we just use a voltage divider formula. We just use a voltage divider formula. And really, we're taking a look at this value here. And by the way, this is a unitless number. Why is it unit? Because I'm dividing voltage by voltage. Okay? So the voltage in and the voltage out is called what we call the gain. The gain of this filter, okay, is A. It's a unitless value. Gain is unit because it's volts divided by volts. So let's just go up here. Okay? So if I studied the output here, and I studied the input, and I put them together, I could calculate the gain. So gain for anything, actually for anything, is V out divided by V in. There you go. That's also for efficiency, right? Gain and efficiency are pretty much the same. And as you know, efficiency is a unitless number as well. So although you can look at it as though efficiency, you better be calling it gain, because that's the term we're going to be using moving forward. A low-pass filter. A low-pass filter works as we just discussed earlier, okay? So it just says, in any case here, this is a low-pass filter, by the way, because if it's a very low frequency, I'm going to get a high voltage out. Guess what? If I wanted to build a high-pass filter, I just put the resistor here and I put the capacitor there. But we'll get into that in a second. I know I got 20 minutes left in this lecture, so I'm kind of watching the time. So essentially, if we take a look at a low-pass filter, so in that, if I have those two frequencies, okay? If I have these two frequencies, hold on. There. And I want to put that into an amplifier, into a microphone. And then I want to put it through a frequency, want to put it to a filter, and I want to get rid of the high. I want to attenuate the high, and I only want to hear the low. I'm going to build a circuit that looks like this. And then my input is going to be those two frequencies together. And then I'm going to study them here. And I am going to be studying the output. And the output's going to look like this. So any of the high frequencies are going to be they're going to have a low amplitude. And I'm not even going to hear them. Any of the low frequencies are going to have a high amplitude. But there's this kind of filter pass in here. I mean, I'm going to choose this so that right around here is going to be that frequency of my low G harp. Okay, I'm gonna that whatever that note was, that was actually blowing on the first note, so it's a G. So that low G right there is going to be pretty much where I want it. Somewhere in here, I want that low G, because I'm not interested in any of the frequencies kind of below that G or after that G. Now those other high pitch frequencies are going to be over here, right? Because that was my F. They're going to be way over here. You're not even going to hear them. It's going to be really cool. So it's not like we're having all of these frequencies come at once. There's just the G, and there's the F, And the G kind of goes through, and it whatever comes in, that's what comes out. But the F, we're not even going to hear it. There you go. So now this FC thing is really important. Okay. So at this point, this is what we call the cutoff frequency. FC is the cutoff frequency, and that's why there's a lowercase c there. So I mean, and there's a subscript of C. There you go. So that's the corner frequency, or the cutoff frequency. Sometimes we call it corner, sometimes we call it cutoff. It's cutoff frequency. And what's going on here is that anything after this is going to be severely attenuated. It's going to be below 70.7% of the amplitude. So the amplitude is going to be really low. And generally, we've got to say there's some kind of value where the cutoff is. So we got to be able to calculate that. And there's a formula here, actually, that's pretty cool. Like if you kind of look at this formula, I kind of rearrange it for the XC formula. It's almost the same. You can play around with that if you want, but I just need you to know this formula. This is kind of one of those formulas you actually have to remember. I mean, maybe I could be cool if I did another video to describe the actual formulation of this formula and where it comes from and how it works and the physics behind why it looks like this. That's really cool. I can do that. But right now, I just need you guys to understand that that is how it is. Please do. Okay, that's cool, Dylan. So someone remind me about that, okay? Someone give me the heads up. Dylan, say, Lars, you were going to do that video on why this, so I don't have to just remember this stupid formula. But right now, I'm going to just move forward. So remember this stupid formula, okay? And it's a great stupid formula. It's called for the cutoff frequency. And this -3 dB, decibels are like awesome. We don't need to get into decimals. I mean, decibels. I'd like to kind of do some decibels. It's not required to move forward here. Really, we're looking at kind of my amplitude here. Decibels are like kind of a really cool concept, especially when you get into logarithms and stuff. But again, that's another video that I kind of have to do. I should put on my YouTube channel for sure. But moving forward, this is really cool. If I wanted to know the corner frequency, if I wanted to know the cutoff frequency, I could just do this, dude. It's dependent on the resistance and the capacitor. Obviously, if I have this resistance and this capacitor, and I change the frequency here, then my output is going to change, and it's going to change like this, and this curve is going to be dependent on the resistance and the capacitance. There you go. So that's what's going on. It's actually, it comes from this formula, which is really cool, but we replace XC with R, and I can explain that exactly why in my little video there, but that's cool. So this is kind of a neat word, attenuation. To attenuate something is to kind of, I'm going to use the word throttle because we are talking about that in pneumatics to some degree, because I did use the word throttle, the air in pneumatics, I think in my last lecture. And we're going to use that word a little bit more. To attenuate something, we're just making it smalling. We're making it smaller. We're attenuating it. We're taking, actually, we're killing the efficiency that creates whatever the output is. And then we make it smaller. We attenuate it. Attenuation is also, we can increase it and decrease it. Attenuation kind of can be a dial to actually attenuate something, but we won't get into that. That's just a term that we're using to significantly attenuate something, which means that we're going to make its gain, this value here, we're going to make it get lower. Here we go. So here's an example, dude. Essentially, we got a low pass filter, and here's some formulations here, and you guys can see me use this formula. I'm just going to go over this quickly. We're going to calculate the corner frequency, we're going to calculate the gain, and we're going to calculate the gain, these two different gains. So essentially, what we're going to do is we're going to calculate the gain at 100 hertz, and then we're going to calculate the gain at 1,000 hertz. And we're going to see, because it is a low pass filter, that the gain at 1,000 hertz is going to be much more than the gain at 10,000 hertz. Okay, good. So essentially, we've got all this value here. This guy is the resistance, and this guy is the capacitance. We don't actually, this is really cool. We don't have to calculate the capacitive reactance of this. We don't have to do that, because the formula, this formula right here, it doesn't require capacitive reactance. Dude, that's so awesome. Really? This is such a simple calculation. Exactly. So my corner frequency here is going to be this guy. Okay, my corner frequency here. So essentially, when I'm graphing this, if I'm making this graph with a resistor with a certain value and a capacitor with a certain value, the corner frequency, the value right here, is going to be this many hertz, That's my corner frequency. That's not actually telling me what the gain is at 100 hertz. That's not telling me what the gain is at a 10,000 hertz. I'm just saying, dude, when I get to this many hertz, my amplitude will be attenuated to the point where it hits 0.7. It's going to be 70%, 70.7. It's going to be 70% of my output when I hit this frequency. So this particular filter, this particular low pass filter is actually, it is any frequency below this, it will pass through. Any frequency after that, it will not pass through. And here we go. We're going to calculate this guy, but in this case, we're going to need to calculate the voltages here, and we're going to need to calculate this and this. Actually, we don't actually have to calculate the voltage because, the resistance and the voltage out is directly in alignment, in phase with the reactance, and the voltage in is directly in phase with the impedance. So we don't actually have to calculate voltage. We can just use these guys. Now we'll see the voltage divider formula kind of jump in here. What I'm going to do here is I'm just going to calculate my AV at 1,000 hertz. For me to do that, I have to know what the capacitive reactance is. I calculate the capacitive reactance. It's pretty high. Okay, at 100 hertz. At 100 hertz, it's 15. Okay, so now I'm going to calculate my Z because I have to calculate my Z because my formula requires Z. I calculate my Z, and my Z, I need the resistance and I need the capacitive reactance. I throw it into my formula and I get 15. Oh, dude, this number and this number are almost the same. Well, that's really cool. Okay, wait a second. So now my V out is going to be all of this. So what is this all about? Dude, my V out is going to be equal the voltage drop across my XC. Again, here we go. The voltage drop across here is going to be here, but it's also equal to this. It's also equal to this. Now, why is it equal to this? Do you see it? Do you see it? This guy here, dude, this guy right here is the voltage divider formula. Let me try this again. Voltage divider formula. Let me grab on this guy. Dude, the voltage divider formula, that's what that is right there. Look at it. 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 Okay, VXC, the voltage drop across the capacitor, is equal to the voltage source times the resistance of the capacitor divided by the total resistance. Or in this specific case, the voltage drop across the capacitor, VXC, is equal to the voltage in, which is the voltage source, divided by the reactance, multiplied by the reactance divided by the impedance. In other words, the resistance of the capacitor divided by the total resistance. And we know the resistance of the capacitor is called reactance. We know the total resistance is called impedance. Dude, this is the secret pretty much to this whole lecture. This is like the Holy Grail right here. If you understand that, you really get this. You really understand what's going on here. As I change the frequency, the resistance of this changes. I can just use the voltage divider formula to calculate the gain. So I'm using the voltage divider formula here, and I can say that this guy, the AV, the actual gain is the V out divided by the V in. I know what my V in is. It's labeled. It's over here. It's given. Whatever. Was I given my V in? V in. It doesn't actually. Was I given my V in? Did it say? It doesn't actually matter what my V. That's the really cool point. Actually, this is what am I talking about? This is really cool that we don't need to know the V in. We know that it's in phase with Z, and the V out is in phase with XC. So I can just use XC instead and Z instead. Actually, yeah, we can see this through the voltage divider formula. You can just use XC and Z because this is the same ratio as this. These two, whatever they are, will give you the same. If you divide this by this, you'll get whatever ratio it is divided by this because they're in phase. And that's because we can use Ohm's law now. So in this case, what I'm going to say is I'm going to use the resistance here and the resistance here, and I'm going to see that they're almost close to 1. So at 100 hertz, the gain is almost 1. At 100, here it is. The gain is almost 1. It's almost here. Now, again, if we do the exact same math and we put in 10,000, we're going to go down here because my gain is going to be 0.22. I'm not even going to go over that, dude. That's just that you just walk through it yourself. Okay, that's good. And again, my video over here walks you through that, and I do all of the math for examples. So those are really good. Now, this is a semi-log graph. Okay, so what's going on is that we're dealing with a logarithmic scale. We're dealing with a logarithmic scale. The reason we call it semi-log is because this scale is logarithmic and this scale is not. This scale is linear. It's directly linear. It's just, this is just 0 and this is 1. So this indicates a gain of 1. And by the way, gain has no unit. So this side has no units. It's just a gain, okay? This side is frequency. Obviously, it's in hertz. So we can see over here, if we plotted this, if we actually went ahead and used these numbers, okay, all of this number and all of this circuit right here, and we plotted all of the frequencies, they would look like this. And that is called a Bode plot, okay? So when we're doing a Bode plot for any kind of filter circuit, it looks like this. Now, get this. I'm just going to move forward, and I'm going to say a high-pass filter, we can see the corner frequency formula is exactly the same. Actually, almost all of the formulas are exactly the same, except for the one for gain. Because we're actually changed the geometry of our circuit, we're no longer studying the voltage drop across the capacitor like we had in our last circuit up here. We're studying the voltage across the resistor, which is down here. So although our corner frequency value formula is the same, and all the other formulas are actually the same, when we calculate this guy, we're studying the voltage drop across here, or more specifically, when we're studying the gain, we take the resistance and divide it by the impedance, and that's it. Now, the way I remember the difference between a high-pass filter and a low-pass filter is that in a low-pass filter, the capacitor is low. In a high-pass filter, the capacitor is high. Simple. So there you go. You switch these around and you get a high-pass filter. So only the high frequencies will have high output and the low frequencies will be attenuated. And the pass band, the stop band, and the pass band look like this. And now I've got this guy looking like this. And if I did the math, it would all be the same. And it would just calculate. Here we go. These are just all of the answers here to do all of the math. I'm not even going to do the math because it's the exact same math. In this case, if I use the same values over here, as I did, actually think the other one was 10K, right? Let's just go up here. No, that was 680. So different values, actually. It doesn't matter. But in this case, I'm using a high-pass filter, and my values are here. If my values look like this, okay, I can calculate if I've got 0.1 microfarads and 1K, my corner frequency will be this. It's a little bit lower. And my gain at 100 is going to be ridiculously low. Like I'm barely going to hear anything. Like you're not going to hear anything. But at a really high frequency, whatever the output is, it's going to be really efficient. And that's what that looks at. Now, I've got another 6 minutes to throw another concept at you called the bandpass filter. And no, I'm not going to stop. But just chill with me here. Look at this. Essentially, in this case, anything that's a high frequency, if I pretend I'm playing my harmonicas, we're going to hear the F. We're not going to hear the G. Over here, if I had this situation here and we use this filter, right, we're going to hear my G and not my F. But what if I had an in-between? What if I had a G, a C, and an F, and they were all playing? What would happen if I wanted to hear the C? Because the F is high, the G is low, and the C is in the middle. A, B, C, E, F, G. E, B, C, D, E, F. You know what? That's weird that I'm saying that because you guys don't understand why a G is actually lower than an F. A, B, C, F, G. It just believe me, it is. You know what? I'm just going to play them for you so you believe me. I know that's weird because a G is actually after, like F, G. F should be. Wait, here we go. That here is my. Here's my F, and here's my G. There you go. So just believe me. So So there you go. So what if I needed a C that was in the middle? Okay, so here's my C in the middle. There's my C in the middle. So if I wanted that C and I wanted to hear it, I would build what's called a band pass filter. I would put a low filter and a high filter together. This is a low pass filter. As we can see, it's got the resistor here and the capacitor there. I put a high pass filter, which is a capacitor with this capacitor high and the resistance low. And I put this together, and my output will target that C note. No kidding. Again, this is what's going on here. I've got over here, I've got my corner frequency 1 and my corner frequency 2. And these guys are actually the same. This to calculate this value, you just calculate the corner frequency for the low pass filter. And for this value, you calculate the corner frequency for the high pass filter. And that's it. And you just put them together. It's like, to do all of the math for this, you have to do all of this stuff twice. That's all you have to do. Just do it twice. You get the high pass, you get the high corner frequency, the low corner frequency, and then from there, you can go ahead and applications. Yeah, well, you know what? This is a really cool application here. This is really cool. We're actually dealing with power supplies. So I'm just going to pause on this for a second, and then I'm going to stop this, and I'm going to talk to you for the next 3 minutes and let you guys go. So this is called a bandpass filter, where we have maybe a frequency that is quite specific, and we want to tune just that frequency. There's a whole like that. You know what? Even let's just say that person, that Bob in the middle of the room of all those 100 people talking, let's say he had his frequency of his voice was right in the middle range of everybody else's. We would have to use a bandpass. If his frequency was really high, okay, Bob's like just got a really crazy high voice, we could then use a high pass filter. If Bob had a really crazy low voice, we could use a low pass filter. But if he had a really specific voice, it was just tuned to a very specific frequency, we could use a band pass filter. There you go. So that, I know that's crazy, guys. There was a lot of stuff going on. It's important that we understand these things, because moving forward, we're going to use these in application in sensors so that we can listen very specifically. We can tune our sensors to certain frequencies. And it's just really important just generally to understand how capacitor reactance, impedance, and resistance work together, because we're going to deal with something called power factor when we actually start running inductive loads, because inductors also do all of everything we just talked about. But instead of a capacitor, we use a coil instead. And you can actually use those. One more application I wanted to talk about was those amplifiers. I'm actually going to pull it up. I'm going to pull it up. Equalizer stereo images. I'm going to pull this up so you can actually see this. So, because we got like a couple minutes left. Here we go. So stop that. Cool. This is what I have on my stereo, guys. I got one of these. I got like an old school one. So it's like probably, whatever, 25 years old or something. Kind of looks like this. Maybe not this fancy. But essentially what's going on here is that each one of these dials, let me just go for one that's there. That's a nice simple one. Each one of these dials here is actually a bandpass filter. It specifically tunes in. This tunes in 500 hertz. This tunes in 1,000 hertz. This turns in 2 kilohertz. So all of these are specific. They only allow anywhere just really close, maybe a little bit above and a little bit below 500 hertz. And that's it. So then you can amplify just the 500 hertz. And that's how those equalizers work. And that's when you're taking music and you're just tuning in very specific kind of bits of the music where you really want to hear the highs or the lows or the mediums or the mid ranges. They all use bandpass filters. Each one of those has its own bandpass filter. And each one of those has a little, what we call amplifier or operational amplifier. So with that said and done, thank you for watching, guys. What we've just covered is we've just talked about the fact that we're using the nature of the changing resistance or reactance of a capacitor. We're putting in a series circuit, and we're seeing with the voltage divider formula, with Kirchhoff's voltage law in a series circuit, we're seeing that as this changes, the frequency changes, the resistance or the reactance of the capacitor changes. And if we put them together in a certain circuit, we can actually get a filter that the amplitude out changes depending on the frequency. And again, everything we're talking about is AC. So AC is information as well. It's not just this AC thing. That can come from a sensor, or it can have a very specific signature to it. We can put that in there and tune out very specific signatures. Dude, that's all I got. Okay? That's no more. Okay? We're stopping now. Just go do the homework, study it, and watch that video of me. And the video is called, what's the video actually called? Okay. The video is called RC filter circuit. That's it. So on Lars Explains, RC filter circuit, or sorry, right in the PowerPoint there. Just click on that and watch me on the board actually doing some calculations.
Okay, bye.